energy on board, right? So they don't need to eat phytoplankton, they don't need to eat the water column. They've got all their energy on board, so they spend less time developing, less time in the water column. They probably are eaten by predators less because they're up there less, but they also have a lower dispersal distance. So they're often only in the water column for hours to days. Some of the less trophic species only disperse maybe just a few meters, up to maybe hundreds of meters. Right, so plankton trophic, small, little energy investment from the parent means they have to eat a lot in the water column, longer development times. Less trophic larvae, larger, lots of energy investment from the parent. They don't have to eat to develop. They spend less time in the water column, disperse less distance. And then we have a third, essentially it's a non-larval type, but it's called direct development. Right? There's no actual larval phase. So the larvae emerge as juveniles. Excuse me. There are very few of these individuals produced at any one time because we're talking about lots of energy investment in the maternal individual, allowing this larvae to go through a direct development either inside the female or inside an egg that it has to partition with lots of energy. All right, so high energy investment and a very low number of offspring at any one time. So when we think about the number of offspring, the most, any one time, planktotrophs, so planktotrophic organisms produce the most larvae per reproduction effort. Less trophic, somewhere in the middle. Direct development, the fewest per reproductive effort. So when we think about organisms that have direct development, there are three different kinds. So there are viviparous species that bear live young, like us. They're ovoviviparous, that bear live young, but these young are incubated in eggs inside the mother. Lots of sharks are like this, so they actually give birth to live baby sharks, but they actually develop in eggs inside the female. And then there are oviparous species. They actually lay eggs out of which the young develop and hatch out of the sharks that do this as well. All right, so viviparous, ovoviviparous, and oviparous. And just to reinforce those three major larval types, just in graphical form, so you've got your planktotrophs, lessithotrophs, and direct development larvae. So essentially the distance here is showing you the time that these different larvae spend up in the water column, right? So the planktotrophic larvae, from the time they're spawned from your bottom-dwelling invertebrates, they spend a lot of time up here in the pelagic region feeding on plankton before they settle back to the substrate. Your lessitotrophic larvae spend a much shorter time up in the plankton, not feeding, just developing before they settle back to the substrate. And then your direct development larvae spend no time up here in the plankton. They just are laid or are hatched from the mother right directly as juveniles before they turn into adults. All right, just to give you guys an idea of what some of these different planktotrophic larvae look like, they're super crazy. So this larva here is actually the larva of an urchin. And that looks damn near nothing like an urchin. Maybe you could say those look like flies. And you can see that there are lots of different ways to be a planktotrophic larvae. And the reason these areas are highlighted here, all these blue areas here, are the rows of cilia that these individuals use to feed, right? So they use this ciliary action to catch things out of the water column as well as to move around in the water column. So they use ciliary action to move around and catch food out of the water. And just to give you a good idea of the diversity of larvae just from fishes. So these are bony fish larvae from species here in South Florida. I mean, damn, that doesn't even look like a fish. It's like an alien. That, I think, is the larvae of a pufferfish, and that is super cute. Looks like a little Pac-Man. So these guys will stay in the water column for weeks to sometimes months before they take on what we think of as some kind of adult-ish body plan. And one of the cool things about these bony fish is that they have a strategy that's somewhere in between the planktotrophs and lessithotrophs. So often the eggs that are fertilized to make these fish larvae actually have a yolk sac in the beginning so it kind of gets them through the first couple stages of development early on. But then, for the rest of their life as a larvae, they have to feed in the zooplankton and eat food to go through their growth and development before they turn. And I wanted to say one thing about this life cycle, the different stages of being a larva before you turn into a juvenile and an adult, and that lots of invertebrates have really complex life cycles and lots of different larval stages that have different food requirements. So this is the life cycle of a copepod. So here's your male and female copepod, your egg and sperm. So all these different stages are different stages of larval development. So you've got two different stages. There are your nuclei stages. There's your copepodid stages. So some really bored zoologists a long time ago spent a lot of time staring under the microscope, categorizing 5 different stages of larvae that ended with the same to me. But one of the ways they categorize them is what they eat, right? So these guys are all different sizes, so they're probably going to eat different size food. But when you have a complex larval life cycle like this, it means that at any one of these stages, where they were requiring different types of food, they could not find that food and not have enough food to make it to the next stage. So the more complex life cycle you have, the more likely you're not going to reproduce successfully, which means you're not going to get your larvae through to the adult stage. So these more complex life cycles of marine invertebrates, the more complex you are, the more likely that you're going to have boom and bust recruitment cycles, which means some years are going to be great because all the types of food that your larvae need are there, and you're going to recruit in gangbusters. In other years, you'll have almost zero recruitment because one or many of these stages not going to have enough food around for development. So one of the big questions for marine biologists early on when they started to study the reproduction of fishes and invertebrates is that these individuals are making hundreds, sometimes thousands of larvae at once, and a small fraction, maybe just a couple of percent, actually make it through to the next generation. So that's a huge investment of energy for a little bit of return on getting your genes back into the population. So one of the classic questions is, why do you make so many larvae if so many of them are going to die? And 3 answers that all seem to be equally good and all have some support, all revolve around kind of spreading the risk around. Right? So the more larvae you make, the more likely that you are to have a few of them make it to the next generation. Because one, all habitats aren't created equal. That means all of your larvae aren't going to land in good places. Some of them will, probably most of them won't. So making lots of larvae means that at least some of them are going to find a good place that has the right temperature, currents, and food sources. Food is going to be patchy, especially up in the water column, up in the pelagic region. We'll talk more about that when we talk about phytoplankton. And the more larvae